Let us now see types of data structures. So our data structure is classified into mainly two types: primitive data structures and non-primitive data structures. So non-primitive data structure is further classified as linear data structure and non-linear data structure. Okay, so as we have already discussed, primitive data structure operates on primitive data types. It operates on primitive data types. So we have different primitive data types for primitive data structure that are integer. For real, we have in C float and double. For characters, we have char data type. For boolean, we have boolean data type. For integer, we have int data type. Right? So primitive data structure operates on primitive data types. Non-primitive data structures are constructed using primitive data structures. So in non-primitive, it is again classified as linear and non-linear data structures. So non-primitive data structures are constructed using primitive data structures, and non-primitive data structures again classified as linear and non-linear data structure. We will see these two data structures in detail. Linear data structure is again classified as static linear data structure and dynamic linear data structure. Whenever we want to store elements in sequential manner, we will use linear data structure. Okay? Non-linear data structure does not follow sequential storage of data. In static data structure, memory is allocated at compile time. Means we have to fix the size of arrays before we can run the program. Okay? Dynamic means memory can be allocated at runtime. So, we are not required to specify size of linked list, stack or queue at compile time. So, stack, linked list and queue can be allocated memory dynamically. Okay. So, in linear data structure, mainly we have arrays, linked list, stack and queue. These are the four linear data structures. In non-linear data structures, elements are not stored sequentially. They do not follow sequence. Okay. The example of non-linear data structures are graphs and trees. We will see all of these data structures in detail now. So, let us discuss about primitive data structures. So, primitive data structures operate on the fundamental or basic data types which are supported by a programming language. Some primitive or basic data types are integer, real, character and boolean, as we have already discussed. Pointer is also a primitive data structure as it operates on primitive data types. Now, non-primitive data structures are those data structures which are created using primitive data structures. For example, array, linked list, stack, queues, trees and graphs. Non-primitive data structures can further be classified into two categories, which is linear and non-linear data structures. Let us see linear data structures and non-linear data structures. What is the difference between these two? If the elements of a data structure are stored in a linear or sequential order, then it is a linear data structure. Okay, so whenever we want to store elements linearly or sequentially, then we will use linear data structures. For example, array, linked list, stack and queues. Now, this linear relationship can be represented in two ways. Linearly means they may be stored at sequential memory locations. For example, in case of arrays, we store elements in sequential memory locations. For example, if we are storing integers, then integer, assume that integer takes 2 bytes of storage. Okay, and suppose 1 is stored at address 1000. Then 2 will be stored at 1002 and 3 will be stored at 1004. Okay, as integer takes 2 bytes. Okay, so these are what? Sequential memory locations. So one way of representing a linear data structure is through sequential memory locations. Second way of representing linear data structure is by means of links. Okay, why we have to maintain links? Because, for example, elements which I am using, suppose first element is at base address 1000. Second may be at random location, suppose 2006. Okay, suppose this is my second element. Then I need to provide address of this element so that I can form a linear structure. Okay, so by means of these links, we can again create a linear data structure. So these are two ways. So this type of linear structure which is connected through links is a linked list. Okay, so these are two ways to represent a linear data structures. Let's see nonlinear data structures now. If the elements of a data structure are not stored in a sequential order, then it is a nonlinear data structure. So in this, elements are not stored sequentially. The relationship of adjacency is not maintained between elements of a nonlinear data structure. What do you mean by adjacency? For example, in this, if we want to find adjacent elements of 2, then adjacent elements of 2 is 1, which is known as its predecessor, and 3, which is known as its successor. Okay, in this example, adjacent node of 2 is what? 1, which is its predecessor. But this type of adjacency relationship is not maintained in nonlinear data structure. And examples of nonlinear data structures are trees and graph. So let us see all these data structures in little detail. First of all, let's see arrays. Arrays is example of a linear data structure. Elements in memory are arranged in continuous memory. Elements of array are arranged in continuous memory. All the elements of an array are of the same type. If we want to store elements of the same data type in sequential manner, then the suitable data structure is array. Okay, suppose this is my array A and these are 5 elements of array. Then in order to access these elements, we will use index. A of 0 will return first element, A of 1 will return second element, which is 1, and so on. Okay, let's see stack data structure now. Stack data structure, in this structure, elements are stored in LIFO principle. LIFO is nothing but last in, first out. Whatever element was inserted last will be out first. So that's why it follows last in, first out principle. That is, the last element stored in a stack will be removed first. Okay, so this data structure has only one end. Okay, it has only one end for inserting the element and only one end for deleting the element. So using the same end, we can insert or delete data. So in real life, we can associate stack data structure with the rack of CD drives. Okay, suppose we have rack of CD drives in which we are maintaining number of CDs, right? Then first we have to insert first CD, then second, then third, and so on. In order to remove second CD, we have to first delete all the CDs or remove all the CDs from this rack, and then we can access second CD, right? So this is the real life example of stack data structure. Another example can be stack of plates which are arranged in a box. If we have a box and we have different number of plates in this box, then this can be the example of stack. One more example of stack data structure is undo and redo operation. Okay, so if we are writing in word processing software, suppose hi hello, okay, then whatever we are writing will be maintained in an undo stack, hi hello. Okay, but what if I want to cancel out this entry? I want to do Control Z on this. So I have to pop this out from the stack, and whatever will be popped will be stored in a redo stack. Okay, so I'll pop this entry from the undo stack and insert this into redo stack. What if I want to retain this hello again? Okay, if I want to retain this hello, then what I have to do? I have to redo this operation. So in that case, what we will do? This thing will be again moved into this undo stack and we will retain that entry. Okay, so this is the example of stack data structure. Let us see about queue data structures now. Queue mimics the real life queue. Okay, if we are going to ticket counter, then it is a queue data structure. It follows FIFO principle, that is, first person who wants to buy tickets is entered in queue, and after buying tickets, that person is out first. So whatever is first goes out first. So it works in the FIFO principle where the first element stored in the queue will be removed first. So it has two ends. One end is called rear end, from which we can insert elements one by one, and another end is called front end, from which we can remove elements. Okay, so from front end elements are removed, and from rear end they are inserted one by one. So first of all 3 is inserted and 3 is removed, then 1 is inserted and 1 is removed, then 2 is inserted, 2 is removed, like that. Okay, so next data structure we will see is linked list data structure. In linked list, data elements are connected through a series of nodes. And each node contains the data items and address to the next node, as we have discussed earlier, right? We have a head node, which is the first node of the linked list, that contains a pointer which points to the address of the adjacent node, which is a sequential node in the list. Okay, and this is how we will maintain links to the upcoming nodes. Okay, so this is example of linked list. Let us see nonlinear data structures now. In that, first is graph data structure. Each node is called a vertex. So these are nodes and they are called as vertex. And each vertex is connected to other vertices through edges. Okay, so these are different vertices and they are connected through this straight line that is called as edge. Okay, so this is edge between two nodes. So these are two vertex and this is the edge. So this type of structure is called graph data structure, in which elements are stored randomly. It does not follow any sequence. Okay, so real life examples of graph data structures are maps. We can define different maps from one source to destination. There may be different paths, okay, and they may be represented using graph. Okay, let us now see tree data structure. Tree is also a collection of vertices and edges. However, in tree data structure, there can only be one edge between two vertices. Okay, so suppose we have these two vertices, so there can only be one edge between these two vertices. Unlike graph may have cycles. So between these two vertex, we may have two edges. But in tree, there will be only one edge between two vertices. Let us see some terminologies of tree data structure. This is called a root node. This is called the left child of the node. This is called right child of the node. So in that case, this node can be a parent node also, right? The nodes at the last level are called as leaf nodes. Okay, this tree can be called as left subtree, and this tree is called as right subtree. So these are some terminologies associated with trees data structure, and we will see all these in detail afterwards. Okay, so real life example of tree data structure is folder system. Suppose we have this parent folder. In that, we can again make two different folders. This folder may again contain 3 files. Okay, this may contain 1 file. Okay, so this folder structure is real life example of tree data structure.